Okay, let's start. Um, the team says I uploaded the wrong video um, for Monday. So, well, I either uploaded the wrong video or that must be it. Um, Possible I could have copied the wrong link in Blackboard. That's not likely. Anyway, it'll take me some time to fix that. So, um, but I'll do that. So, sorry about that. Let's see. This is where we're at on the homework, right? We have this homework on functions of multiple variables, right? In particular, most important function of two variables. So that was due tonight, but I delayed that a little bit till Friday. If you needed more time to work on that, and then we have this short homework on limits and continuity. And then this key homework next week on partial derivatives, which is what we're talking about right now. Okay, so that's really an important homework for us. So we're finally doing differentiation, right, in the context now of three dimensions, right, in particular with functions of two variables. Okay, and most people find that really straightforward, and so I mean, at least the paper and pencil part is kind of straightforward. The analytical part, thinking about it geometrically or graphically, can be a challenge just because you're in three dimensions. And so we're going to try to visualize that in class. But of course, the homework will be mostly devoted to things you can carry out by hand on paper, right? But that is usually pretty straightforward. Okay, for calculus 3 students. Sometimes it might be a little bit tedious, but because it involves differentiation, and sometimes differentiation rules can be tedious, um, but um, but otherwise it will, I think, seem kind of familiar. At least this homework, it does get a little bit more involved. Well, maybe starting today, okay, but not too much worse. Uh, all right. So anyway, that's where we are in the that's where we are in the homework. All right. Don't let me forget to get to pass the robot today. I thought I heard you say something. You sent me a question, but you must have answered your own question. All right. Okay. So all right. Um, are there other questions about the homework that you guys want to ask right now? This homework? Well, any of these actually, but this one's kind of the most urgent one. Trying to Yeah, I was the wrong video was posted. Probably the notes are correct, but the video I think is wrong. Um, I think the video was. I think I do that kind of quickly. So I think when I was clicking on the video to upload, I chose the one from the 5th. That was probably the last one that was I could see in the dialog box, and, I wasn't paying attention to the date. So, um, uh, but probably the notes are right. But so that's the very first question off this homework. Oh, okay. I didn't discuss that actually. Usually in an algebra class, you spend a lot of time talking about is this curve really a function, right? So is y really a function of x? And you learn that conceptually, and then you learn some shortcut rules for determining that, right, in 2 dimensions. It's kind of the same in 3 dimensions as well. So they're giving you an equation, right? In this case, in 3 variables, of course, because we're in 3 dimensions now, right? And then they want to know is z a function of x? So what that means is if you pick a particular choices for y and z, I'm sorry, for x and y here, right? Okay. So in other words, if you choose a point xy on the xy plane, will you be able to determine a unique value for z from this equation? So does that lead to only one and only one value for z? Okay. Because if you pick a point here, x and y, and input it into the equation, and there's two possible associated z values for that choice of x and y, that means it's not going to be it's z is not a function of x and y. Okay, for each input, for each point in the xy plane, which is a pair of numbers, right? But that still is considered a single input. That point must get one matching output, so only one z value, right? Yes. Now, geometrically, what that means is I can't draw a picture of it. Okay, I can draw a picture of it in 2 dimensions. But it's this is, I can describe it to you in 3 dimensions, but it's harder to draw in 3 dimensions. I don't have because I don't have a handy picture already drawn. Let me add here. Okay, so in 2 dimensions, right? You're often asking, is y a function of x? Usually we think of y as being the output variable, and x is being the input variable, right? Okay, so conceptually what that means is for any choice of x in your function rule, usually it's a formula, for any choice of x in your function rule, do you only get one matching value for y? Okay, so graphically how that comes out is if you have a graph like this, for instance, right? Remember this, Elijah? So if you have a graph like this, then y is not a function of x, right? Okay, because you can pick an x value here, right? On this curve that would lead to 2 different matching y values, right? So in this case, we would say, oh, y not a function of x. Write that symbolically like this if you don't want to write it out in words. Okay, so y is not a function of x. And then, however, for function curves, right? You can have a lot of different curves for functions, but you don't have this situation occur, right? For each choice of x you make, right? If you have a function, then that leads to one and only one matching y value, right? So in this case, it is true, y is a function of x. Now, how does that translate to 3 dimensions, right? If we're trying to answer the question, is z a function of x and y, right? Okay, so you might be able to determine that from the formula. And if you're given a graph, you can usually determine it from the graph, but it's harder to construct the graphs, right, than it is in 2 dimensions. So let's look at the formula, though. What was that formula? Somebody have it available? Do I need to switch back? So x times z squared plus 4xy minus y squared equal 7. Okay, it can be 0 would work just as good. I don't know why they put 7 there. All right, so what we do is let's solve this equation for z. So let's write it in this form. Okay, let's write it in kind of in more traditional function form where we have the equation solved for z. All right, so that takes a little bit of work, right? But what happens? So we get, let's move these 2 terms over to the right-hand side. So I'll get x times z squared is 7 minus 4xy plus y squared, right? And then I'm trying to isolate the z. So we'll divide everything by x, right? To get the x out of this term. So I get z squared is equal to, and then this comes out looking kind of ugly, 7 over x minus, here when you divide by x, the x's will drop out, right? So you'll just get 4y. And then here you'll have y squared over x. But now this is z squared, right? Okay. So I don't want z squared, but I want just z. So how am I going to get z there? take the square root. But that's where the problem is going to come in, however, because when you take square roots, right, you have a positive and negative square root. So you have to write z is plus or minus 7 over x minus 4y plus y squared over x. I bet when you choose, I bet, for instance, when you choose x to be 1 and y to be 1, for instance, if you look at that input, you'll get, so what happens when, so in other words, what is f of 1, 1 here for this function? Let's see. Can y'all tell me that? Can we do that math in our head quickly? That would be what? 7 minus 4 plus 1? Is that 4? And we're taking the square root, right? So we get what? Plus or minus 2? Oops. See, that's bad, right? Okay. For this input, you have 2 different matching outputs. So not a function. So the answer is no, I think. Okay. I think, well, Elijah, you were thinking ahead of me. So you probably, when I first started talking, figured that out, right? Okay.
I did the same. So, I mean,
okay. All right. So now, geometrically, though, Elijah, what does this mean? So when you graph, if you're able to make a graph of this equation, so you'll get a surface, right? How would you tell that that surface is not a, how would you tell that surface? For that surface, z is not a function of x and y. See, here, you know the famous test, right? It's called the vertical line test. So if you have a curve, right, and you can draw a vertical line that hits the curve in multiple places, not a function, correct, right? Okay, so what's that? What's the analog test here in 3 dimensions? Yeah, so it's the same thing, right? If you draw a line that is perpendicular to the xy plane, see, okay, vertical line is perpendicular to the x-axis, right? So see here, if you draw a line perpendicular to the x-axis, if it hits the curve in multiple places, not a function. Well, for 3 dimensions, if you draw a line perpendicular to not just the x-axis, but the xy plane, okay, you'll get a line going straight up and down, right? Like the z-axis happens to be perpendicular to the xy plane. But if you draw any line that's perpendicular to the xy plane, and if it hits the surface in multiple spots, not a function. All right. But again, that test is that test is easy to illustrate for, people in beginning algebra right now. Well, maybe college algebra, right? That test is easy to, but it's not easy for me to demonstrate that corresponding test in 3 dimensions. So we do have to think about it a little bit more conceptually in 3 dimensions. All right. So, okay. So I think I said everything there is to say about that. All right. We're not going to, that's a good conceptual question from college algebra. We're not going to spend so much time dwelling on that. Most of the time we'll be dealing with z is going to be a function of x and y. Okay. At least for these upcoming sections. Okay. All right. So yeah, so I think there the answer is no. And then these questions are a little bit tedious, right? But they're not difficult there. You're just evaluating functions of 2 variables at lots of different inputs, right? Remember, you can use symbolic inputs as well. All right. So don't get confused when you're using symbolic inputs. Any other questions there so far? I've worked on this. Okay, so you have a little bit of extra time, right? It's not due till Friday. So I think the first question, well, I don't know, maybe it's not the same answer for everybody's first question, right? It's easier to see when it isn't than to demonstrate that it is, okay? Because to see that to see that a surface is not a function, you just have to find an example of an input that gives you multiple outputs. But to demonstrate that it really is a function, you would have to somehow convince yourself that for every possible input, that might be the entire xy plane, right? So for every possible input, you're not going to get multiple outputs. That's sometimes harder convince yourself that that's true. Okay. Um, all right. Okay, so let's switch back to the notes and pick up right where we left off last time. So we were doing last time what is called partial differentiation, but we haven't actually named it partial differentiation yet, but that is what we are doing. And so we're going to look at another example. I'll have you do some of this example, but we'll start off here because first one is it says graph, but we're really not going to graph. I'm going to show you the graph. You don't really have to do this by hand. So here we have a function, right? And this really is a function. So in this equation, z is a function of x and y, and so it says. So of course, when you graph that function, you're going to get a surface, right? But we want to know what is just a portion of that surface look like. So if we fix y equals 2, if we set y to be 2 in this formula, okay, then what we really have is, so when you set y equal to 2 in this formula, you'll leave x and z as variables. But if you set y to be 2, then notice the y's are going to disappear from the equation, right? So then you'll just have an equation z equals to some function of x. So you have a function in two variables, and you can graph that curve. That will give you a curve. So so that's the question. So what does the curve look like, or what is the formula for the curve if we fix in this equation y to be 2? Well, that's so easy, right? All you have to do is substitute 2 for y, right, in the formula. So you get z is equal to x squared plus, what is that? X squared times 2, right? Plus 2 squared, right? Over 5. And so if we simplify that a little bit, this is x squared plus 2x squared. So that's, normally you would write that as 3x squared, right? Plus 4 over 5. It's fine to leave it just written like that. Let me break it up, though, into two terms, just to remind you of what this curve looks like. So when you graph this curve, right, in two variables, z and x, what sort of curve do you get? What sort of curve is that going to be? Do you recall? That's a parabola, right? Yeah, so that's just a quadratic function. You just have x squared, right? So that's just a parabola. Okay, so now, so where is that parabola at? That parabola is embedded in this surface. Okay, that parabola is embedded in this surface. Let's see if we can see a picture of that then. So I think if I graph this properly, we'll never know if I did because I'm not going to check it. But I think I graphed this surface way down here somewhere. Oh, here it is, way down here. Okay, and what we were doing is so this is the z-axis, as usual, right? That's the vertical axis, but it's not labeled here, right? So here's the x-axis, and here's the y-axis in this picture. And what we did was we fixed y to be 2, right? So on this surface, we're just peeling off all the points where y is equal to 2. Well, here's y equal 2. I think right there is y equal 2. So this curve that I have graphed here, which hardly even looks like a curve, right? You can't see the curvature very much, but this is that's it. This is the curve. What was it? 3/5 x squared plus 3/4, or yeah, 3/5 x squared plus 4/5. So that's this curve embedded in that surface. That whole surface is that graph of that big formula. Okay, so when we fix y equal 2, I think here's 2 on the y-axis. So if you just go up from there, right there would be on the surface. That's all the points where y is equal to 2. So see, notice that's just a curve, right? Okay. That's just the curve. When you change your values for x, right? Here we have x running from -2 to +2, then the z values are going to change. Unfortunately, because of the perspective on this surface, you cannot see, you can't see much curvature there in that curve, but that's supposed to be a parabola. Okay, so we're kind of from a really bad perspective, but that really is a parabola. It's not a very that's kind of a that parabola is kind of flat anyway, because of that coefficient on the x squared is, what is it, 3/5? So that kind of flattens out the parabola anyway. So you get kind of a I don't know what the word is there. Okay, not a very steep parabola anyway, and we're looking at it from a really bad perspective. So, but there it is. All right. Now, see, once you have got that, once you have established that curve, right, then you can ask calculus questions about that curve. So, for instance, you can ask about the slope of this curve, right? Okay, as you're moving from left to right along the x values, right? Or from right to left, if you want, if you want to think of it that way, through the x values, right? That curve has a slope, right? And so the slope of that curve, the direction of that curve, can also tell you about the direction of the surface, okay? Because the curve is embedded in the surface, right? But it only tells you the direction of the surface it only tells you the slope of the surface in the direction of the x-axis, right? So you know that moving parallel to the x-axis, you can use your calculus 1 knowledge to figure out what the slope of this surface is, right? Well, you know, if this is a parabola, of course, okay, then if you know something about the slope of the surface already, you can visualize. Well, you know something about the slope of this curve, so you know something about the slope of the surface too. But of course, we can answer questions precisely about the slope of this curve by using our calculus knowledge, right? So I think that's what we're going to do in the next part. So let me let y'all do that, okay? If I can find it again. Here we go. All right, so do y'all have keep in mind, right? There's the curve. And so we want to know what's the slope of this curve when x is equal to 2. All right. So what's the slope of this curve, not the surface, right? But what's the slope of this curve when x is equal to 2? All right, so I'll do that really quickly. Okay, I'll get that really quickly. What are we going to calculate first here to answer this question? The derivative, right? You'll calculate the derivative of this equation, right? Okay. So in other words, you're going to find z prime. We're thinking of z as being a function of x here, right? So we'll calculate z prime. So easy. Just have to use the power rule here, right? So you bring the 2 down times the 3/5. So that's going to be 6/5, right? And then you'll have x to just the first part because you'll subtract 1 from that exponent. And of course, what's the derivative of the constant? 0. And then, so to find the slope of the curve when x equal 2, you'll just evaluate your derivative at x equal 2, right? In other words, you're going to find z prime of 2. That's one way of writing it on paper. And that would be equal to 6/5 times 2, which is 12/5. That's a pretty big number because that's a pretty high slope, right? That's 2.2, right? So no, 2.4, right? So um that's pretty steep, but you really don't get that picture. You really don't get that feel at all when you look at the graph. Okay, where is the point? So here's the point 2, right there on the edge of my graph. There's the point 2, right? Okay, and so at that particular point, right, that curve is it's fairly steep because it's going as you increase x, right? Your z value is supposed to be going up by 2.4 every time you increase x by 1, right? So that thing is really coming up, but you just but the way it's graphed is just distorted that, right? Okay. It just doesn't look as steep as it really is. So what you know is, right, you know here, right, what's the slope of the surface in the direction of the x-axis, right? Parallel to the x-axis, what's happening to that surface? It's going up, right? Okay. At that rate of 2.4, or you can think of it as we're going in this direction, the surface is going down at a rate of 2.4, right? Okay. Um, from this particular point. Okay. Let's try another portion of that surface and answer the same sorts of questions here. So do y'all have that formula written down? This function? Because we're going to look at a different piece of that surface. All right. So let's find the equation for the curve when x is equal to 2. Okay. Let's find the equation for the curve when x is equal to 2. And it says graph that curve. We'll go back and graph that in just a moment. Is that also going to be a parabola? And then we want to find the slope of that curve when y is equal to 2. Oh, so that's back at the same point we were at the moment, right? X equals y, right? And then answer the same question, right? What is the slope of the surface in a particular direction once we do part C? So see if you can do those really quickly, right? You got to find the equation for the curve first, and then when x is fixed at 2, x is fixed at 2, right? Find the equation for that curve. Then you want to differentiate, right? I'm gonna start passing out the roll. I keep forgetting. Oh, man, you're back. All right. So if you're still working, that's fine. let's start here. What is the equation if we fix x to be 2? So what do we get here if we fix x to be 2? So you just plug 2 in for x, right? So you get 4 plus 4y plus y squared. Is that right? 4 plus 4y plus y squared. So z equals 4 plus 4y plus y squared. Of course, it's all divided by 5, right? So again, what sort of curve is that? If you graph that in 2 variables, what are you going to get? Know what that thing is again? It's still a parabola, yeah. Anytime you have a quadratic function, that is where the input variable is just raised to the second power. I'm talking about in 2 variables, right? If your input variable x, or in this case y, is just raised to the second power, that's it. That's quadratic. Right? And when you graph that, you're going to get parabola. So you're going to have some parabola, right? It might be shifted around a set of axes, but it's going to be a parabola. And since the coefficient on the y squared is positive, right? That's plus y squared over 5. That means it's opening up, right? So that's parabola. That were negative y squared. Okay. So we know we're going to get a parabola. Here's actually what it looks like. Since we have the surface, we can trace out where x is equal to 2. That's a little bit easier to trace that out on this surface because of the way the graph is drawn. So x equal 2 is right here on the edge. Right there on the edge, I think, is x equal 2. Maybe it's actually maybe it's inside the edge, but anyway, I drew it on the edge. So there's x equals 2, and see, indeed, that is a parabola, right? Okay, right. So you do have a parabola. And I believe could be a parabola. It looks like it could be a parabola. We know it is a parabola. And you are even it looks like we're a little bit beyond the vertex of the parabola, right? It looks like we're on kind of describe that as the we're on the right side of the vertex, right? Because it looks like the vertex of this parabola is down here, correct? Okay. So we appear to be on the increasing part of the parabola, right? So I'm expecting that when we find the slope, it's going to turn out positive. Okay. So over here, the slope is going to be negative, right? Because we're to the right of the vertex. Their vertex is somewhere about right there. And then over on the right side, so that that portion of the parabola. Is that what happens? Or have I just am I just getting fooled again by the picture? So easy to do, especially with this surface. So what does the derivative turn out to be there then? So what is z prime? Yeah, just z prime equals, what is it going to be equal to there? 2/5 y plus 4/5. So 2/5 y plus 4/5. Yeah, I think you're right. Okay. Because when you differentiate z, right, you are going to get in the top, you'll get 4 plus 2y. The first 4 disappears, right? Because that's a constant. So you get 4 plus 2y over 5. And then if you just break that into 2 terms, you get 2y plus 5, right? And if you evaluate that at y equals 2, then indeed we get, what is that, 4/5 plus 4/5? So we get it 8/5, which is positive, right? So indeed that curve is increasing, right, at the point y equals 2, right? Okay, and it's increasing at this particular rate. So now we can answer a simple question about the surface, right? What's the slope of the surface in the direction of the y-axis at this point? where y equals 2 and x equals 2. Well, that's exactly the point that we were dealing with in the previous problem, right? I mean, in the previous part, we were thinking about what is the slope of this parabola when x equals 2, because that's the parabola when x equals 2, right? And here's y equals 2, right? So the slope of this parabola will be the same as the slope of the surface in the direction of the y-axis, parallel to the y-axis, right? Because this curve is parallel to the y-axis, right? Then this surface is increasing at that rate of 8/5, right? Now, in other directions, right, the surface is not increasing at the same rate, or maybe not increasing at all, right? But in the direction of the y-axis here, right, parallel to the y-axis, from this point, the slope of the surface is 8. Okay. So now we know how to find the slope of the surface, at least what? In the direction of the x-axis, right? And in the direction of the y-axis. Right. So from a particular point on the surface, you know how to find what's the slope of the surface parallel to the y-axis, and what's the slope of the surface parallel to the x-axis. All right. You do that by holding either y constant or x constant, depending on whether you want to find it, whether you want to find the direction parallel to the y-axis or the x-axis, right? And then you differentiate. So let's summarize that then. Let's summarize our knowledge. Okay. All right. So look, we're grown-ups here. All right. So so we can think of a whole thing, x constant or y constant, in a function of two variables. We can think of holding the x constant, or we can think of holding the y constant without actually choosing a constant value for x, or without actually choosing a constant value for y. We do that in our minds, right? Okay, because we're familiar with algebra, and so we don't have to say, okay, I'm going to substitute 2 for x, right, and then differentiate, or I'm going to substitute 2 for y and then differentiate. Right? We just think of that mentally, conceptually, right? I'm going to I'm going to let x be some constant value, but I don't have to specify which constant value. Or I can let y be some constant value without specifying exactly the value that I had in mind, right? That abstractly. And then we can differentiate, okay? So this process is called partial differentiation. That's exactly what we were doing in those previous examples, except now when we think of holding y constant or holding x constant, not going to choose a particular value for y. If y is a constant, or not going to choose a particular value for x. Just think if x is a constant. All right, so look, here's what we do. All right, or here's the notation. Right. So if you're going to think of holding y constant, right, in this function of two variables and then differentiating, here's the notation that we'll use for this. Okay, so this is called the partial derivative with respect to x. All right. So in the partial derivative with respect to x, x is still a variable, but y, we're thinking of that as being a constant, right? So when you think of y as being a constant, right, the formula reduces to just a function of x, right? The y is a constant. So in your formula, just have a function of x and then differentiate with respect to x. Right? So in modern notation, this is the notation for that process. Right? In calculus 1, you're differentiating, right? prime here, right? Okay. But remember, in calculus 1, you only have one variable. All right, okay. But here we've got two variables, x and y. So we don't use the prime notation. Instead, we use that subscript. Okay. So that means y is being held constant. We're differentiating with respect to x. X is still a variable. Now, this is modern notation, but of course, partial differentiation has been around for a long time. Okay, so this was developed for modern function notation. So the old-fashioned notation for partial differentiation looks like this, right? It's kind of like the dy dx notation from calculus 1, which is also old-fashioned notation. But notice we don't use the d here. We use this little stylized d. Okay, it's kind of a backward 6, right? That's what it looks like. It's supposed to look like a d, but not really a d. Now, I don't know why they just didn't use d. I don't see issues, but they wanted to emphasize that this is partial differentiation, not regular differentiation. Right? So, right, how do I read partial z, partial x? I would still say x. Right? Same thing. That means partial differentiation with respect to x, right? That bottom, that denominator tells variable differentiate with respect to. Or if you don't want to put z, since z is the same as f of x, you put f of x here as well in place of z. But all those things mean the same thing. Okay. And this is the derivative of this function f when y is thought of as a. Just thinking of y as being held constant and differentiating with respect to the one variable x. If you can also hold x constant, right? So if you hold x constant, then you're differentiating with respect to y, and you get parallel notation, right? Except it involves y instead of x. This means that if function x is not but let's draw a picture of that. Because the pictures are very nice, all right? And they're the same pictures that we drew earlier with specific example, right? So look, if you are calculating the partial derivative with respect to x, right? Partial derivative with respect to x, what you are doing is you are holding y, right? You can think of that, right, as taking a plane that is a constant value for y, right? In other words, a plane that's parallel to the x-axis. It's a plane where y is held at a fixed value. And intersecting that plane with your surface. When you intersect that plane with your surface, of course, what do you get? You get just a intersect the plane with the surface. What in here? Just a what? Not a line, but a curve. Or it could be a line, right? Okay, but you just get a curve, right? Okay? And then this derivative is really the derivative of that curve. Okay, that's what that partial is. And of course, that curve has tangent lines, right? And so the derivative value at a particular point, right? The slope of tangent. So that curve, that particular. Notice that tangent line is parallel, though, whereas in the direction it's actually. And so, what this partial derivative with respect to x shows you is the slope of the surface direction of the axis. Direction of the axis. Now, if you hold x constant, just doing kind of the opposite, right? We're intersecting a plane here which is parallel to intersecting a plane, let me see, also perpendicular xy plane, right? But parallel to the y-axis, intersecting that plane surface,
And when you do that, of course, you get a curve. And so you take a curve, okay, and get slopes or tangent lines for that. So the derivative of a function, partial derivative with respect to y, this gives you the slope of the surface in the direction of the y-axis. Direction of the y-axis. Now, one thing to keep in mind, right? That so one question we cannot answer. Remember, so you have you know the slope of the surface in the direction of the y-axis. We know the slope of the surface in the direction of the x-axis. And answer those questions with partial. Don't know. What about slope of the surface in other directions? Directions that are not parallel to the x-axis, not parallel to the y-axis. Suppose we want to know the slope of the surface in this direction, not parallel to the x or the y-axis. How would we find that? Okay. That question we had to consider. No, can't be in the direction of z, right? Okay, all right, not the direction of z. Z is just straight up and down, so that's just straight up and down through the surface, right? Okay. But you could intersect this surface planes that are tilted, right? They have to be perpendicular to the xy plane. So that would give you a curve, right? Again, and maybe not parallel to the y-axis, maybe not parallel to the x-axis, but on the surface in some other direction. How do we find the slope in that direction? So, okay, so just starting with a simpler question that we know how to answer. All right. Well, let's try it here. I don't have a picture for this one, unfortunately, so we're just going to have to be imagining this, right? So, so this says, what? Here's a function of two variables. X is e to the x squared y, e to the x squared y, and I think the y is, wow, that's really ambiguous, but I think the y is supposed to be in the exponent here, okay? I think the y is supposed to be the exponent here. That's e to the power x squared y, right? And so this says what? Find the partial derivative with respect to x, right? And then evaluate that at point 1, natural log of 2. Okay. So that's kind of a weird point to be evaluating. So probably chose that on purpose. Somehow make calculations easier. Let's see what happens. Let me lower the screen here so I can write more easily. And let's try calculating then that partial derivative. Okay, so remember, you're thinking of, fortunately, you're thinking of y there as being a constant, right? So the only real variable in this formula is x. Now that still presents some challenges though, right? How are we going to differentiate this formula? Again, where x is the variable. So you're just thinking of y as being a number, 1, 2, 3, something, right? Doesn't matter. What differentiation rule will we have to use here to do that derivative? What? I think the product rule, right? I don't see how to do it without the product rule, right? Because here we have a product there of expressions, right? Of expressions involving x, right? So I think we're going to have to use the product rule. All right, well, let's see. Do I remember the product rule? How does that work? It's pretty easy, right? Don't you take the derivative of the first factor times the second, right? Just keep the second. So what's the derivative of x, though? 1. Oh, that's nice. So you just get 1 times e to the x squared y. Ooh, that wasn't bad. All right. And then you add on to that, you just reverse that process, right? So you keep the x, and then you take the derivative of e to the x squared y. Okay, whoops. So how do we take the derivative of e to the x squared y? But remember, the y is just a number. The y is just a constant, right? So it's not really going to make much difference to your differentiation. So how do you differentiate exponential functions? Do you remember? Like e to the x squared. Yeah, remember, it's going to duplicate itself, right? So you'll get e to the x squared y, but then what's the catch here? You have to then also multiply in the derivative of the exponent, okay? You have to multiply in. So that's the chain rule, all right? But in general, just remember, if you have e to an expression, and you want to differentiate it, right? You repeat e to the expression, right? You repeat that, and then you multiply by the derivative of the expression that's in the exponent. So we have to multiply by the derivative of x squared y. But remember, y is a constant, right? Y is just a number. So what's the derivative of x squared y? Well, you just bring the 2 down, right? Times the x, and you're just going to keep the y. All right, see the y. Nothing happens to the y there. Okay, you just keep the y. See, if that was x squared times 3, right? You would just bring the 2 down, but you would keep the 3, right? Okay, well, that's the same thing. Y, we're thinking of y as being a constant here. So you just get times 2xy. Let's see, let's clean this up a little bit. So this is what? E to the x squared y plus, is this what? 2x squared y? E to the x squared y? So, you know, a little bit messy, but it was easy to calculate, right? Okay. You know, derivatives are easy to calculate if you just remember your differentiation rules. Okay, now I'm supposed to do something with this though, right? I want to evaluate this at what point? 1 natural log of 2. Does that make things easier here? Maybe. So I get e to the 1 squared times natural log of 2. So that's going to be e to the natural log of 2, right? Plus 2 times 1 squared times natural log of 2. I'm not going to write the 1 squared, right? And then e to the 1 squared, so that's 1, and then times natural log of 2. Oh, so this really is pretty easy. Because what is e to the natural log of 2? 2, yeah. Remember, these functions are inverses of one another. E and natural log are inverses of one another, right? So they cancel each other. So you just get 2 here, and plus, and then 2 times the natural log of 2, and then this is going to be 2 again, right? So you get another 2 thrown in there. So you get 2 plus 4 natural log of 2. Not bad, okay? So what is that telling you? What's that number telling you? At this point, right? At this point on this surface, whatever that looks like, I didn't graph it. At this point on this surface, right? The slope is this number, but in what direction? So what does this partial derivative give you? Which direction? In the direction of the x-axis, right? Okay, so parallel to the x-axis, this is the slope of your surface, all right, whatever that number is. Okay, it's not a very big number, so that number is the slope of the surface. So parallel to the x-axis, you're going up, right? Okay, from this point. As x increases, you're going up from this point, right? Okay, or as x decreases, you're going down from this point, because this slope is this slope positive? Yeah, I think that slope is positive, right? All right, let's try it. Let's try it again though. But now let's take, this is still partial derivative, okay? So this is the archaic notation, partial derivative
of f with respect to y, right? So let's evaluate that at the same point. So let's see what the slope is in the direction of the y-axis. All right. So we have to do our differentiation again. Is this easier? Oh yeah, this is way easier, right? So partial f partial y. I'm not going to write fxy. Let's just write. Y. And so what is that? So you're thinking of the x as just being a number, right? You're thinking of the x as just being a number. So what is this what is this function really reduced to? What is this really like? Yeah, it's really just kind of e to the y, right? Yeah, it's really just e to the y, because remember, x squared is just going to be a number, and the x there is just going to be a number, right? Okay, so this is very similar to just e to the y. Okay, so what's the derivative of that going to be? Well, you're still differentiating the exponential function, right? Right, you still have an exponential function here. You have e raised to an expression. So how do you differentiate this? Don't you just repeat this, right? So the x just goes along for the ride because that's just a constant. So you get x e to the x squared y. You repeat this, but then you have to remember also to multiply in what? Yeah, what, Robert? Yeah, the derivative of the power. That's right. You have to multiply in the derivative of the power. What is the derivative of the power, though, Robert? What? No. Yeah, no. What is it, Jose? X squared, right? It's x squared, correct? Yeah, it's x squared. See that, right? Because this is a number times y. A number times y. So if you take the derivative of a number times your variable, what's just you get left? The number, right? If you took the derivative of 3y, your derivative would be 3, correct, right? Okay, so here you have x squared y. X squared is just a number, so its derivative is x squared. So let's see, cleaning that up a little bit, it looks like this is going to be x cubed e to the x squared y, but that's still really easy to evaluate when at this point, correct? So very convenient to evaluate that at this point. Let me show you how you would write that, by the way. In this archaic notation, you would write this like partial f, partial y, evaluated at, what's the point? 1 and natural log of 2? Right. So you put that vertical bar, and then you put your input there as a subscript to the vertical bar. So this notation was developed by Leibniz, not Newton, but Leibniz developed this notation. You see, it's really clumsy, right? Okay, but it's very useful. So despite being a little bit cumbersome, it's still useful. And so it's still in use because it's still useful. This is the more modern notation, though, not developed until probably not until the 20th century, early 20th. Okay, so well, anyway, what does this turn out to be? Well, you get 1 cubed e to the 1 squared times the natural log of 2. Well, all those ones are just going to disappear, right? And what is e to the natural log of 2? We just said a moment ago, right? That's just 2. So all that just substitute. So the slope in the direction of the y-axis is 2. Not much different than this, actually. So also a positive slope in the direction of the y-axis. All right, let's go back and try this one again. Okay, so this is that same surface we were looking at a moment ago. But let's not look at the surface because the surface is very confusing. Let's just do it here. All right, so find that partial with respect to x.
think we actually already did that, kind of, right? So find the partial with respect to x and then evaluate that at minus 2, 0, then give some interpretation of that, right? Okay. So find the partial derivative of this with respect to x and then evaluate it at minus 2, 0. Remember, you're thinking of y. The number. X derivative as the number. Yes. So zero. That's not help, right? That's the second. Back to minus 2. So I see the one little tricky part was what I had already expected for some of you. So when you're differentiating this, right, with respect to x, you're thinking of y as being a constant, right? And that's the first time you do that, it's a little bit you have to think about it, maybe. Okay. And then after that, you'll like it because it's going to make the differentiation much easier. See, when you're thinking of y as being a constant, well, y is not involved in this term. So the derivative of x squared, of course, is just 2x. You can just keep the 5 in the denominator here. Elijah was asking, do we need to use the quotient rule here to do differentiation? The answer is thankfully not, because the denominator is just a constant. If this were 5x and that or something like that, that would mess things up. Okay, but since the denominator is just a constant, you don't have to use the quotient rule. You can just differentiate the numerator there. Okay, so the derivative of the second term is just going to be 2. Bring the 2 down, right? So you'll have just 2xy. But now here's the nice part. The derivative of y squared with respect to x, that is 0. Because with respect to x, y is a constant, right? Okay, it's just a number. So the derivative of the third term is just 0. Remember, derivatives of constants are 0. So see, when you take the partial derivative with respect to x, you're thinking of y as being a constant. So you just get, well, you just get this, right? And now when you evaluate that at, what is it, -2 and 0? Well, just plug -2 in for x, and the 0 in for y is nice because that zeroes out this term. So it looks like you just get the first term here, 2 times -2 over 5, right? -4/5. So what does that mean to us? That tells us at this point, this surface is decreasing because this slope is negative, right? At this point, this surface is decreasing, but in what direction? Yeah, in the direction of the x-axis, right? Okay, in the direction of the x-axis, this surface is decreasing. Well, at this rate, actually, in fact, right? Okay, but because this slope is negative, in particular, the surface is decreasing, but in the direction of the x-axis, parallel to the x-axis. So it may be doing something different parallel to the y-axis, right? Well, here's the question, parallel to the y-axis, but unfortunately, it's at a different point. All right, so let's differentiate this. So partial z, partial y, right? Okay, in other words, the partial derivative with respect to y. Let's see, what's that going to come out to be? So we're thinking of x as being a constant here. So what is this derivative when x is a constant? Well, what's the derivative of the first term? 0, right? Okay. And then what's the derivative of the second term? The power rule does not apply here, right? Because x squared is really a constant. So all you have here is a number times y. That's the easy, almost the easiest type of derivative, right? What's the derivative of a number times y? Just a number, which is x squared, right? See, if you were taking the derivative of 2y, you know the derivative would just be 2. Well, here you're taking the derivative of x squared y, so the derivative is just x squared. The last term is a little bit harder, though, right? That derivative is 2y, right? There you are going to use the power rule. All of this over 5, okay? And now let's evaluate that. Whoops, got ahead of myself there, right? Let's evaluate that at this point, 1 minus 2. So we get, well, not too exciting, right? 1 squared plus 2 times a minus 2 over, is that also minus? Oh, no, not quite, right? I thought that was also going to be -4/5, but I forgot about the 1, right? So you really have, is it -3/5? So also at this point, not the same point though, at this point, also the surface is decreasing, but that is in the direction of the y-axis, right? Okay, so parallel to the y-axis is also, the surface is decreasing. All right, now, here's a good challenge question. This is an important question. So, and you'll see why, okay? So we want to find a point, on this surface. So 1 minus x minus 1 squared minus y minus 2 squared. So that looks like that's some sort of quadratic surface. I wonder what kind of quadratic surface that is. That's some sort of quadratic surface. And but anyway, for that surface, we want to find where the slope in the direction of both x and the y-axis is 0. So of course, what important thing happens on curves? What important thing happens where its slope is 0? Yeah, you get maxima or minima there, right? You get peaks or valley points, right? Where the slope is 0. Okay. So something similar to that must be going on this surface, right? Okay. Maybe. So we're looking at where the slope in both directions, right? Parallel to both the x-axis and the y-axis, right? Where the slope in both directions is 0. So how would we answer this? You all answer. How would what you do? That's right. Oh, exactly. Set each to 0, and then see if you can deduce from that, okay, right? A point that makes both of those 0 simultaneously. So see if you can find a simultaneous solution to those two equations. The two equations David said was take the derivative with respect to x and set that to 0, and take the derivative with respect to y and set that to 0. These two equations, see if you can find a simultaneous solution to these two equations, that is, x and y values that will make both of these 0. Well, I think if you write down those equations, you find the simultaneous solution pretty quickly, right? So set both of those partial 0, 0. Figure out how to satisfy both of those equations at the same time. Very careful about your equation. It's not that hard. Remember, do not expand the x minus 1 squared or the y minus 2. You don't need to expand that differentiation. Okay, you could, but not necessary. For a while, it's about the same. Careful. Yeah, what you're doing is oh, not next time. Now, so, so Okay, let's do it here. I think y'all are. Sometimes you're um, forgetting how easy the differentiation rules really are and making it harder than it is. All right. So that means you were traumatized somewhere in calculus 1, I think. Okay. So all right. So if we take the derivative here with respect to x, but it's very similar with respect to y, right? Because this formula is kind of symmetric. So the derivative of 1 is 0, right? Because that's a constant. So there you get a 0. And for this term, since we're differentiating with respect to x, well, we're going to use the power rule, right? Because you have an expression raised to a power. Anytime you have an expression raised to a power, remember, you can use the power rule to differentiate that. Okay. By the way, remember, it doesn't matter if the exponent here, if the power is a whole number like 2, or if it's a fraction, the power rule still applies. That is Newton proved that. Okay. The early founders of calculus all knew that, right? How to do that differentiation with a if you had a fraction here instead of a whole number power. But Newton was the one that proved that was true. Okay, so the power rule applies here. So you can bring down the 2, right? You just keep the expression x minus 1, but the catch here, always the same. See, this expression you must multiply in its derivative. Okay, but what is the derivative of x minus 1? 1. So it really don't have to do anything, right? Okay. If that were x squared minus 1, then you would have to multiply in something a little more complicated, right? So whenever you have an expression, it could just be plain x, but it could be any expression involving x raised to a power. You differentiate using the power. Okay. So you bring the 2 down. But now what about this last term? How do you differentiate that? 0, because that's a constant, right? So differentiating that with respect to x just gives you 0, and then we're going to set all this to 0. So when we solve that, what does that turn out to be? X equals 1. Yeah. So we just get x equals 1. Oh, nice. So we know that the answer to this point, the x coordinate is 1, right? Now let's also take the derivative here. With respect to y, it's going to be very similar, right? The derivative of this term is 0. The derivative of this term is 0, right? And then here you bring the 2 down, and you have to remember to multiply by the derivative of y minus 2, but that's still 1. So that doesn't really change anything. And so do we also get y equals 1 here? What is it? Oh, minus 2. Okay. So, well, we can still make that mistake of copying down things wrong. So is it y equals 2 here? Yeah. And so there's your point. Apparently at that point, the derivative in the direction of the y-axis and the derivative in respect to the x-axis both 0. So that strongly implies that this should be some sort of peak or valley. Here's the picture. So indeed, that's what it is. Okay. There we have a peak. Oh, cool. All right. So there we discovered that surface. Now, it is possible that you have very weird surfaces. So it is possible this might not get peak because it means that the surface comes up here, up in this direction, Oh, weird surfaces like that. You create weird surfaces. So sometimes get full. That also happens. Hmm? Well, so what is that point? Is it what you want? Yes. So okay. Now you know, of course, with in calculus 1, of course, you can compute higher order derivatives, right? So you can compute the derivative of a derivative. That's the second derivative, right? And we can also do this in
with partial derivatives as well, except it's slightly more complicated with partial derivatives. So let me explain why. But let's stop here for a minute, okay? So let's take a few minutes. We'll come back at maybe 12:57 or something, and then we'll finish off here showing you how to compute second order or higher, or mostly second order, but higher order partial derivatives. And they're going to tell us the same thing as higher order derivatives in calculus 1 told us. That they'll tell us about the curvature of the surface, okay, the cavity surface. All right. So, but before we dive into that, we need to get a drink of water or something. So I'll come back in about 5 minutes and we'll look at examples of this. Okay. So we resumed here. So again, when you take the partial derivative of one of these two variable functions, right? You take the partial with respect to x, or also the partial with respect to y, right? These are also functions of two variables. So that means they also can be differentiated, right? Okay. So this function of two variables, you can then compute the partial derivative of this function with respect to x, and you get what's called the second partial derivative, right? Okay. Notice, so this is the old-fashioned notation. So notice in the old-fashioned notation, right, you get d squared f, all right, above dx squared, right? That has to do with how the notation is applied, right? When you're computing these partial derivatives. So this indicates a second partial derivative where we took the partial derivative with respect to x twice, right? You can also write that down in a more modern notation, just writing the subscript of x twice. So we don't usually put an x squared here in the subscript, although I guess we could, all right? So that means also taking the derivative with respect to x twice. If you take the derivative with respect to y twice, right? Okay, well, you can do that. Now, however, what's different for these functions of two variables is we can mix up the order in which we're taking the derivatives. So you can first take the derivative with respect to one of the variables, for instance, y, okay, right? That's just a function of two variables now. And then you can take the derivative of that with respect to x. So when you do that, you get what's called a mixed partial derivative. So taking the derivative with respect to one of the variables and then switching and taking the derivative with respect to the other variable, right? So this is what it looks like in the old-fashioned notation. Notice this means in the old-fashioned notation, you took the derivative with respect to y first and then the derivative with respect to x. So notice you're sort of reading the order of differentiation from right to left, in the old-fashioned notation. But in the modern notation, we do it differently. We list the order of the derivatives from left to right. So this means I took the derivative with respect to y first, and then I took the derivative with respect to x. All right. So there's a difference there between the modern notation and the old-fashioned notation for mixed partial derivatives. So of course you can do it in the other order as well. You can take the derivative with respect to x first, and then the derivative with respect to y. So in the old-fashioned notation, it looks like this: derivative of x, then derivative of y. You still have the d squared here in the top, right? But in the more modern notation, you would write it like this. This means we differentiated with respect to x first, and then differentiated with respect to y. A nice thing happens, though, if you differentiate in either order. I'll show you why. I'll show you what I mean in just a second. let's just take an example here. So let's find all second order partial derivatives for this function. Don't know what this looks like. So 3xy squared minus 2y plus 5x squared y squared. That is not a quadratic function. So you're not going to get a quadratic surface here, because this term has to be 3. Add up the powers of the exponent. So that's 1 plus 2 is 3. This one has 4. 2 plus 2 is 4. So that's not a quadratic surface. I don't know what sort of surface it is. It's not a quadratic surface. Okay, so let's do these partial derivatives. And the easiest one to start with is just x twice, right? So remember, what that means is you're going to first take the derivative of the partial derivative with respect to x, and then you're going to differentiate again. Okay, so I guess we have to start first, right, by just finding this partial derivative, right? And while we're at it, we may as well go ahead also and find this partial derivative, because I think we're going to use that one as well. Okay, all right. So what is the partial derivative with respect to x of this expression? Now let's see, what do we get from this first term when we differentiate with respect to x? 3y squared. Yeah, it's so nice to hear that, right? You just have this is like a constant times x, right? Like 6 times x. The derivative of that would be 6. Well, here you have 3y squared times x. The derivative with respect to x is just the 3y squared, right? So you get 3y squared here, 0, right? Because there's no x's there. And here you're going to have to use the power rule a little bit, right? You need to bring the 2 down, right? But that's it. So you get 2 times 5 is 10, but the y squared just stays there, right? So you get plus 10x y squared. Oh, not bad. What's the derivative with respect to y? Let's see. So here we're going to use the power rule, right? So we get 6xy. And then for this one, minus 2, right? And then this one, oops, have to use the power rule again, right? So that becomes plus 10x squared y. All right. Don't let me make a mistake, okay? Because things will go awry here if I make a mistake. All right, now let's take the partial again with respect to x. So you look at the first partial with respect to x, right? And then differentiate again with respect to x. So let's see, let's differentiate that formula with respect to x. What happens in the first term? You get 0, right? So that's 0. Of course, the 0 is meaningless. And then here we get what? 10y squared. So we just get, it looks like 10y squared, right? While we're thinking about it, let's do this one. So that means first differentiate with respect to x and then differentiate with respect to y, right? So I look at this again, but now let's differentiate with respect to y. So let's see, the first term would become 6y, is that correct? Bring the 2 down. And here you get, bring the 2 down again, so you get what, 20xy? Ah, not bad. Now let's see, what was the partial derivative with respect to y? Twice. So let's do this one, but now with respect to y. So I get what? 6x, right? This is 0. This becomes what? 10x squared. You differentiate with respect to y. You just keep the coefficient. So you just get 10x squared. And what is the next partial derivative? But in this order, y first and x second. So let's differentiate this with respect to x. What do we get? 6y, is that right?
And then that's 0. And then here with respect to x is that 20xy? Yeah. Ah, there they are. Okay. See, not bad. Well, even though this is not a quadratic expression because you have a degree 4 term here, this is still a polynomial. Polynomials are always easy to differentiate. Okay, even in calculus 1 or even in calculus 3, polynomials are easy to differentiate. It's one of the things we like about polynomials. Now notice that something interesting happened here. See that the partial with respect to x, then with respect to y, turned out to be the same as the partial with respect to y, and then with respect to x. That's no accident. That is always going to be true. Okay, so the second order mixed partial derivatives are equal, and that is summarized, I think, in a statement here. Oh, there it is. Okay, all right. So fxy and fyx are the same. Okay? So there is a condition on that though. Your function has to be continuous. All right. Function has to be, but polynomial functions are continuous. This example, we had a polynomial that those are continuous the entire x line. All right. So this theorem would apply, and indeed, see that it worked, right? All right, guys, now you know what we're going to use second order partial derivatives for, right? We're going to use them the same way we used second order derivatives in calculus 1. They're going to help us with concavity. Okay, all right. So this is where we'll start next time. What if we have this function? Oh, that's a function. This is a terrible example, and I use it over and over again. I really have to need a better example because the surface is so ugly. All right. So if we wanted to explore the concavity of this surface, right, we can do that through the second order partial derivatives. But this is only in the x or the y direction. So we can discover the concavity of this surface parallel to the x-axis and parallel to the y-axis. But in other directions, we won't know what the concavity of the surface is. Okay. And we do it through the second partial derivatives. So let's take that up next time so we can use that as a reminder next time of computing second order partial derivatives, and then we'll see what the concavity is, which is really easy. Once you have the second order partial derivatives, you just plug your point into those derivatives, and if it comes out positive, then it's concave up, and if it comes out negative, it's concave down in a particular direction. Okay, in a particular direction. Okay, all right. So of course, now I can't mention, right? We don't know slope or concavity in directions other than the x-axis and the y-axis, right? So we need to take up that question because we want to be able to find slopes or concavities in directions other than parallel to the x-axis and the y-axis. So how do we do that? Okay, and sounds like it's a complicated question, and it is in a certain sense, especially when you draw a picture of it. It looks complicated, but it turns out to have a surprisingly easy solution. All right, so that's a blessing here of calculus 3. We have a nice theorem to help us with directions other than parallel to the x-axis or parallel to the y-axis. Okay, well, we're done for today then. So you don't have a homework to do to Friday. Don't forget about that homework that's due Friday, though. It was due tonight, right? So if you put it off, that's fine, but don't forget on Friday night it's due. Okay, and I'll see you guys on Monday.